Good morning. We are headed into Chapter 30. Chapter 30 again has got one of those titles that it makes it sound like a lot of stuff's going on. I'm going to say the chapter is, we're going to look at this property called inductance, and we're going to find out that we have one more circuit component that we want to look at. We've looked at resistors, we've looked at capacitors. We're going to introduce something called inductors. Now, the other part of the chapter is AC circuits. Now, along the way, there are these circuits that are oscillating. I'm not sure why they're calling it electromagnetic oscillation. I would drop that. So I would say inductance and AC circuits are the two topics, kind of the big, large scale topics that we're looking at. We're currently in the 4th edition of Giancoli. That's been out for quite a few years now. The previous edition of Giancoli, the 3rd edition, this chapter used to be 2 chapters. There was a chapter on inductance and circuits using inductors, and then there was a separate chapter on AC circuits. Now, when the 4th edition first came out, I took a look at it and I said, I wonder which chapter's missing, and I tracked this down. And then, of course, my next question was, wow, I wonder which portions of the chapter, which sections they left out in order to merge 2 chapters into one. And what I found is they didn't leave anything out. I have no idea why they combined the chapters. So in some sense, I always think of chapter 30 now in this 4th edition as really 2 chapters. Again, one of them is inductance and circuits using inductance, and then we move on and look at general, kind of across-the-board AC circuits. All right, so let's see what we've got here. Now, there was so much stuff going on in this chapter too, I went ahead and just left in the slides that kind of outline the topics. I'm hoping this is helpful. We first look at mutual and self-inductance. This has to do with, well, we'll see, but remember we've got these wires that are going next to each other, and if one of the wires, the current is increasing, well, that would mean that the charges are accelerating, and anytime the charges are accelerating in one wire, they tend to create a current, or an EMF, opposing that effect in the nearby wires. So it turns out that from that, we can create devices based on mutual inductance and self-inductance. Inductance meaning I can make currents in these other wires move kind of without touching them. I can do it by making other currents move in other wires. Very briefly, we're going to look at magnetic field energy storage, how much energy is stored in a magnetic field, and then it's on to circuits. So mutual and self-inductance, magnetic field potential energy, and then we're going to look at LR circuits, the L standing for inductors, LC circuits, LRC circuits, and then finally AC circuits, where we have an AC power supply. And then here's some more stuff. Resonance in AC circuits, impedance matching. These last couple topics we actually aren't going to include. There are some sections in there on impedance matching. Go ahead and look at that if you're interested. 3-phase AC, not essential, so let's get going with mutual inductance. So mutual inductance, again, what's going to happen within mutual inductance, it's, well, you guys remember the transformer, right? So these mutual inductance properties are related to transformers. What we've got is 2 distinct sets of wires, and what this is saying is if the current is oscillating in one set of wires, then the other set of wires will experience an EMF. So we can induce or set into motion a second circuit based on variations of current in circuit number 1. And so we call it mutual. It's an effect happening between one circuit and another distinct circuit. let's go ahead and take a more detailed look at this. So here are the two circuits. So what we've got is current moving through circuit number 1, and then I have a second circuit set up right next to it. So it's a transformer, right? This basically is a transformer. Now, when we talk about mutual inductance, the items that we're interested in here is for current number 1, how much current is coming in, and then how much EMF is going to get generated. Now, what we saw back in chapter 30, when we were looking at transformers, was that there's a couple different ways to think about this. So the idea is, if I set up a current using a set of a coil, a set of loops of wire, if that current is constant, that will maintain a constant magnetic field. So these blue lines coming through are the magnetic field lines that are being generated by the current that we've set into motion. Now, if we set a second set of wires close enough that it can pick up those magnetic field lines, then what will happen is there's the possibility of inducing an EMF. Now, the EMF that gets induced is actually due to electric fields, not the magnetic fields, but Faraday's law says anything we do to vary the strength of that magnetic field will produce looping electric fields, and it's those looping electric fields that will set coil 2, the current in coil 2, into motion. So I'm going to get an induced EMF by varying the current. I've got to vary the current on side number 1. Again, if the current stays steady, there will not be any E field set up due to accelerating charges. So the idea is if I accelerate charges on this side, and acceleration means speed up, slow down, speed up, slow down, either one of those works. And in AC circuits, that's ongoing all the time. We're speeding up charges and then they slow down and go in the opposite direction, pick up speed, speed up, slow down, speed up, slow down, speed up, slow down in different directions. And what that will do is set up electric fields, and those electric fields will set, it'll generate an EMF, and it will set current number 2 into motion. Mutual inductance. Now, the units for this, as long as they've got this here, are henries, which, that's a good name for a unit, right? A henry. And a transformer, it says, is an example of mutual inductance. So let's look at their example. Here is, now this is configured a little differently, but it's basically the same thing. What we've got is, we've got this long solenoid, and it's got N1 number of loops, and that's a bunch, so it's got a bunch of loops here. And then it's got a current, and that current is traveling around the perimeter, the circumference of that solenoid. There's a cross-sectional area, and there's a certain length. Now what they want us to do is figure out how much mutual inductance do we have for this particular setup. And what we've done is we've taken another set of wires, not so many loops, N2, and we've placed it very close to wrapping around this solenoid. So what we want them to do is kind of share the magnetic field lines. Whatever magnetic field lines get produced by current number 1, those field lines are going to pass through the loops on circuit number 2. And really what we're doing is we're making sure these loops fall within the region where there's going to be an electric field, and that it's in reality it's the electric field due to the accelerating charges that are going to set everything into motion. So here's our derivation. So this is the same picture. I think the one before might have been drawn a little better. I hope this is clear after looking at that first one. Let's take a look here. Now the EMF that gets set up in that second set of wires, the second set of loops, By definition, the EMF is defined as the mutual inductance times dI1 dt. So this is for circuit 1, and it's inducing an EMF in circuit number 2. Now from Faraday's law, what we can say is that the EMF that we get is going to be proportional to the number of loops times whatever the flux variation is here. All right, so we can go ahead and calculate that then. So the flux that we get is going to be the magnetic field times the area, and the magnetic field for a solenoid. So we're actually using our solenoid formulas for this particular example. So it needs to be a device, a mutual inductance device that's kind of built like a solenoid, and that allows us to go ahead and use our solenoid formula for the magnetic field. So this is going to depend on 4 pi k over c squared n1 over L times I1. Now, when we convert that into flux, we have to multiply by a cross-sectional area. So if I look at how much flux is passing through each of the loops, so each of those loops, N2, is going to have a flux passing through it, and the amount of that flux will be 4 pi k over c squared n1 over L I1 pi r squared. So that's the area over which we're measuring the flux. Now the flux for a solenoid, or the magnetic field for a solenoid, to a good approximation, we can treat that as all inside the solenoid. Once we look outside the solenoid, the magnetic field drops off very rapidly, and our approximation for solenoids has always been uniform field inside to a good approximation, but the magnetic field is basically zero outside. So again, if I'm doing a flux calculation, I just want to include the radius of the, or the cross-sectional area of the solenoid itself. Now, once I've got this set up, then I can take a time derivative, because that's what Faraday's law is saying. If I do a time derivative, that time derivative will enable me to go and determine how much EMF is being generated in those other loops. So let's do that. What we're going to do is we're going to take a time derivative here. So we look all the way across this formula for flux and go, well, what is there that has any time dependence? It looks like a bunch of constants to me. 4 pi k over c squared, n1 over L pi, they're all constants. The only thing that possibly could be changing here is the current. So again, the idea here is I've got to have the current varying. And so what we're going to do is just take dI1 dt and say the flux is proportional to the rate at which the current is varying, the change in flux. So the time rate change of flux is proportional to the time rate change of current. And there's a bunch of proportionality constants out front. Now looking back up to the formula here then, what we can do is say, hey, m dI1 dt needs to be equal to n2 d phi over dt. So here's my n squared. And then for the d flux dt, I'm going to put that whole package in, and the dI1 dt's go away. So what this says is it doesn't matter, the specifics of how the current is changing doesn't really matter as long as it's changing, as long as there's some acceleration of the charges. And it says that all of these constants combined give me my mutual inductance. So again, we had defined what we wanted to call mutual inductance. And for this particular setup, a solenoid wrapped with N2 loops of wire for a secondary circuit, the mutual inductance is 4 pi k over c squared N1 times N2 over L times pi r squared. Now, if you look to see where the factor of N1 and where the factor of N2 came in, N1 came in, so we're generating the magnetic field effect with N1, and then, so we're using some number of loops to create the fields, and then some number of loops to pick up the effect. And so that's why we get that product, N1 times N2. In our formula, this is generating, well, really the acceleration electric fields, and this is telling us how many of those loops are going to be picking up the effects of the electric field that we've generated. So there we go. Now, again, these are side-by-side wires. So if I get some wires with current accelerating, the wires next to that will get a current induced. That's the mutual induction effect. All right, so what would happen if the coil, if the coils were switched? So what would happen if the coils were switched and we're starting with N2 loops and we're trying to induce current in circuit number 1? And there are theorems that show that the mutual inductance always works the same way in both directions. So that's kind of interesting too. It would be difficult to work back through this problem the other way. It's going to become much more difficult to determine magnetic fields, but we're kind of guaranteed that the mutual inductance effect will work the same way in both directions. So we can drive this from either set of wires, and we'll induce current, induce an EMF in the other set of wires. Well, that was mutual inductance. What is self-inductance? So we define, again, we've got some definitional equations here. What we're saying is, here is Faraday's law again, saying that there's going to be an EMF set up, and we can determine how much EMF by measuring the rate at which the magnetic flux is changing. Again, it's not a causal relationship. It's just saying that there is a theorem that we're able to establish that shows by keeping track of the magnetic field flux, that's enough information that we can determine how much EMF will be generated in circuit number 2. I take that back. This is self-inductance. So this is actually saying I've got a set of wires, and they're going to generate magnetic and electric fields, and those magnetic and electric fields are actually going to have an effect, an EMF effect, on the very same set of wiring. So this is called self-inductance, and let's see how this compares. So in this example, we're going to look at self-inductance, and again we're going to look at a solenoid, but what we're going to see is in self-inductance there's only one set of wires. We're not inducing an EMF in another set of wires, we're inducing an EMF within the solenoid wiring itself. So they want us to come up with a formula, so we'll do that. We'll derive the formula for self-inductance, and then they want us to come back and calculate the value of the inductance given that we use 100 loops, the self-inductance, 100 loops, a length of 5 centimeters, and a cross-sectional area of 0.3. This is tiny, right? This inductor is only that long, and the cross-sectional area is really small, so I don't know, it looks like the size of a AAA battery or something, right? And the solenoid is air-filled. So now, if you flip back and forth, at first you might say, well, we already looked at this, didn't we? Here is a solenoid, here is the magnetic field being generated, numbers of loops, radius of the solenoid, length of the solenoid. But what's different this time is there's not a second set of wires. This is self-inductance, or just inductance. And self-inductance goes by the symbol of capital L. I always feel like capital L gets used a lot when we don't know what else to use. We can't use I for inductance. I is already current. Wait, that didn't make any sense either because we had to use I for current because C was capacity. Anyway, we're going to use L, kind of like angular momentum, right? Why did L represent angular momentum? But we're going to use L here to represent inductance. And we're going to make a definition here. There's a back EMF. There's a reverse EMF generated within the inductor itself. And that's given by the inductance times d I dt. So that's how we're going to define inductance. Now, Faraday's law says that the EMF is going to be given by n times minus n times d phi dt. And we're going to be able to go in and determine at what rate flux is changing. So, very same set of formulas. The flux is going to be B times A. And since it's a solenoid shape, we know that geometry is going to have a magnetic field 4 pi k over c squared n over L times I. And to turn that into a flux, we multiply by the cross-sectional area, and that is pi r squared. Now, again, to get the EMF, we need to be able to take a time derivative of that. Something's got to be changing, and that something is the current. So the only thing in here that really is going to be changing is current. So we're going to speed up the electrons and slow them down, and speed them up and slow them down, and speed them up and slow them down. And each time we speed up and slow down, we're going to reverse directions. So they speed up in one direction and then they slow down, and then they speed up in the other direction and then they slow down. So the electrons are doing this through the wiring. And those are accelerations taking place steadily through that entire process. So if I've got all these accelerations taking place, I know that I'm going to be generating varying magnetic fields, and at the same time I'm going to generate looping electric fields around that region. These are the acceleration fields that we've been talking about. So here is the calculation of the flux, and then here is making it time dependent. And again, the flux will vary proportionally to how the current is being varied. So I could make the current change like a sine or a cosine function. And if the current's changing like a sine or a cosine function, then the flux is going to change like a sine or a cosine function also. So the flux will follow whatever the current is doing. Now, if I look up at my definition of inductance, along with Faraday's law, which is what we're using right now to make this determination, I get an equation that looks like L di dt. That was the first part. And then for the second part, I'll put in the number of loops, and then I'll substitute in the expression that we came up with for the time rate of change of the magnetic flux. So substituting that expression in and setting those equal, now I can cancel out the dIdTs. dIdTs go away. So what we're saying is anytime the current's changing, there's going to be some self-inductance taking place, and the specific amount of L, the inductance, is going to be given by 4 pi k over c squared n times n over L. So there was a factor of n that we used in determining the strength of the magnetic field, and then the question was, well, how many of those loops are going to feel that effect? Well, n loops set up the magnetic and electric fields, and n loops are going to experience the effect. And that's why it's self-inductance, right? It's n loops having an effect on n loops. And so we now have n squared. Now I wrote that as n times n. It looks a little funny. I could have written n squared. But I wanted to make a comparison between the solenoid formula for self-inductance and the solenoid formula for mutual inductance, and they just look the same. The only difference is with mutual inductance, it's N1 loops creating the field and 2 loops feeling the effect. In the other one, it's N loops creating the field, N loops feeling the effect. So it's nice to see kind of the analogy between those. All right, questions? So again, self-inductance is based on this idea. Let's say here's where the solenoid is. Let's say that we have current heading in this direction, and that current is increasing. Well, then what's happening in terms of the charges is I can think of a velocity in that direction as well as an acceleration. If I have charges that are moving here and they're picking up speed, that gives me an increasing current. So think of physics 4A. If I've got V and A in the same direction, that's an acceleration in this direction. Now, if there's an acceleration in this direction, the E fields that are set up are going to oppose that. So in some sense, these inductors, they're kind of self-regulating. What inductors oppose is changes in the current. As long as the current stays really steady, the inductor is fine. It's happy, it doesn't put up any kind of a fuss. But once we try and increase the rate of the current, the inductor says, wait a minute, what are you doing? You're changing the current. I had this nice steady current passing through me, and now you're trying to increase the current. Well, kind of like that. And what happens is the EMF that's generated opposes that increase. So that creates a voltage drop. So when we put these inductors into our circuits, so these are circuit devices, these little loops of wire, we call them inductors. What they do is they create a voltage drop. If the current is increasing, they create a voltage drop along the direction that the current's traveling. So we can add them to our list. Remember, there were resistors. Well, they had voltage drops that were dependent on R times I. There were capacitors. They had voltage drops. That was 1 over C times Q. And now we have inductors with voltage drops that depend on L times di dt. Well, we'll see that. We'll see that show up in some of the circuits that we're headed towards. Now, the other possibility here is, oh, what if the current's going this way, but instead of increasing, the current's dropping? So again, the inductors kind of panic, right? They go, oh my gosh, we had this nice current. It was nice and steady, and now the current's beginning to drop. What should we do? What should we do? And what that corresponds to in terms of the charges is this. The velocity is in that direction, but if the current's dropping off, that tells me that although velocity is in this direction, their acceleration is opposite. These charges are slowing down. That's an acceleration in the opposite direction, or a deceleration. Now, if there's an acceleration, even though the charges are moving this way, the acceleration is back here. And that says that the electric fields that are being generated by these slowing down charges are going to be in the forward direction. So as the charges slow down, they're telling their neighbors, oh no, speed up, we can't let this slow down. And so what makes inductors induct is just taking long sections of wire and wrapping them around so that they're right next to each other. So that if the current begins to slow down, these electric fields that are generated oppose that change. When are inductors happy? I guess. It's when the current's constant, right? If the current's just constant sailing through, there's no effect. You can ignore the presence of the inductor if the current's constant. But if the current is ramping up, then they will create a voltage drop in that section of the circuit, and that has an effect to moderate the change. It's like, oh no, we can't let this happen right away. We're going to have to take our time, let it rise up slowly. And then, if the current in this part of the circuit is slowing down, what the inductors do is they go, okay, we can't let it slow down too rapidly. Let's just let it slow down a little at a time. So that's the effect, and it's all done with, again, the charges are accelerating, and so there are acceleration electric fields creating this effect. And here's just another picture of all of that. So what happens is, in a circuit, it's not only important with inductors to establish which direction the current is traveling, but it's important to establish the direction of di dt. A positive di dt, a current that's increasing, would have a di dt in the same direction as the current. A current that is dropping off would have a di dt that's negative. Now the reason I've drawn those arrows in, if you remember back, we said that within a wire, current can be thought of as a charge per length times a velocity. So whatever the current value is, the current is related to velocity. Di dt is related to acceleration of the charges. And inductance effects depend on di dt. They depend on, it's an effect that takes place when the charges are accelerating. All right, and here's my picture. Here's a wire. Here is the current acceleration. The charges are accelerating in this direction. If the charges are accelerating in this direction, the E fields associated with that will be in exactly the opposite direction. So everybody's trying to reduce the effects of that acceleration. So inductors moderate any kind of variations in the current as the electrons inside either accelerate or decelerate. They generate E fields that either push back or forward on their neighboring on the neighboring electrons. Okay. And that prevents any of them from slowing down too fast. Now you might think, well, how do they do that? Where do they get the energy? Right? I can see that if we're trying to push more current through, sure, they can resist that, but what happens when the current's dropping off? Where is the energy coming from for an inductor to add more energy to the circuit? And inductors store up energy. So during the process, when they were opposing the current increase and saying, nope, not too fast, don't make the current go up too fast, they were stashing energy away. So instead of the current going up quickly, the inductors were taking energy out and putting it aside for whenever the current drops off. And when the current drops off, then they release energy back into the circuit. So they store energy and release it, store energy and you don't know anything else in the circuit that does that? You go, yeah, capacitors do that. So capacitors store energy by building up charge, and then they can release the energy when they discharge or de-energize. So inductors are the same. During the times when the currents are increasing, the inductors energize. They build up a store of magnetic field energy, and then when the currents drop off, they release that magnetic field energy back into the circuit. Those inductors, they're pretty clever. So, of course, what this is making everybody think about is, oh yeah, transformers. It's all transformers again. So if we go back and we review kind of what's going on with transformers, here's a current on one side, here's the current on the secondary side. Now, there are going to be voltages on each side of the transformer. And now that we've introduced mutual inductance and self-inductance, we're set up to where we can go in and derive formulas for all of this stuff, more details showing what's going on. So the transformer we're imagining here, we're going to treat it as if it's two solenoids. Now you could wrap the same wires around the same cylinder, but it's harder to see what's going on. So instead, I built a solenoid over here, and I built a solenoid over here, and then I'm using a continuous O-ring of iron so that the effects, the magnetic effects, are then directed by those spinning electrons, right? Wherever we set up a magnet, we're redirecting the orientations of the electron spins. So I can set up fields over here, and then those fields will get directed over into areas on the other side, and I'll see the same effects. All right, so let's start with, should we start with currents or voltages? It turns out it's easiest to start with currents. So when I'm analyzing a transformer in some detail now, what I'm going to say is that on this side, I have some value of current I1, but it's not constant. I1 itself is constant, but it's got a time-dependent factor. So it's going to be an amount of current I1 that actually varies. So it oscillates back and forth between plus I1 and minus I1, and we'll represent that with a sine function. It turns out that for a transformer, the two currents are in phase with each other. So I can write I2 the very same way. The current on this side is given by some constant I2, kind of a peak current. These are peak values for my currents, or they could also be RMSs, multiplied by the sine of omega t. All right, so that's keeping track of how the currents are configured. Now, what happens then is that these currents are going to generate magnetic fields, and we just looked at this, so these are my formulas for the magnetic fields generated by a couple of solenoids. So I've got solenoid 1, solenoid 2, they're both generating a magnetic field, and since I've got this piece of iron in here, what that's doing is it's redirecting the magnetic field lines so that the magnetic effects don't spread out and kind of, disappear when we get outside the solenoid. Instead, what that does is it reinforces the magnetic field lines so that both magnetic fields are passing through the entire enclosed piece of iron. So now I'm getting magnetic fields everywhere inside that block of iron, and the combined magnetic effect is going to be given by this expression. So when I add the two magnetic fields together, I get a common set of factors, 4 pi k over c squared, divided by L. Now, it doesn't have to match on the two sides, but we might as well say that L here matches L here, and that'll keep track of a factor of L here. What I'm left with then is N1 loops times current 1, N2 loops times current 2, and then since the two sides are in phase, we'll have a sine omega t factor over here on the end. All right. From the magnetic field, then I can calculate the flux. Now remember, when we calculate this flux, it's how much flux each one of the loops is going to wrap itself around. So the flux that we set up inside that iron ring is given by B times A, and we'll say that it's a circular cross-section pi r squared. We're going to make it look as much like our circular solenoids as possible, so that we can see those formulas. So this is the flux. Now it's got the 4 pi k over c squared, pi r squared over L, and then I have the N1 I1 plus N2 I2 sine omega t. We're going to take a time derivative of that, and the time derivative, very same set of constants, but now I'm going to have an omega factor and a cosine omega t. So you can kind of see we're headed towards using Faraday's law to determine how much voltage we'll have on each side. Now this time, instead of thinking this is an EMF, I'm going to think of this as a voltage drop. So EMF, voltage drop, they're going to be the same thing for an inductor. And so the voltage drop across side 1 and the voltage drop across side 2, well, that's going to be equal to this EMF, this reverse EMF. And the reverse EMF is going to be equal to N1 times d phi dt. This will be N2 times d phi dt. So again, we saw this in the last chapter. The voltages are directly proportional to the number of loops on each side. All right, so I plugged everything, and yeah, there's a ton of stuff at this point, right? But it's just kind of the same stuff over and over again. They're just kind of incremental changes from one line to the next in this derivation. But when I see what the voltages are, what I can see is adding this factor of N1 here gives me a factor of N1 times N1. Now that's N1 times N1, and then I'm getting a factor of N1 times N2. Similarly, when I look at the voltage on the secondary side of my transformer, I'm getting a factor of N2 times N2 times I2, and I'm getting a factor of N2 times N1. Now, what I'm recognizing, I guess, is that all of these constants that we've developed for our transformer can actually be sorted out into self-inductance of side 1, self-inductance of side 2, and the mutual inductance between the two sides. That says that voltage 1 is L1, the self-inductance, times di1 dt, plus the mutual inductance from di2 dt. And the voltage on side 2 is going to be L2 di2 dt, and the mutual inductance times di1 dt. So I guess it's kind of remarkable that when we step through all of these, we can show how the voltages on a transformer are proportional to the number of loops, and that the voltages can also be written as a combination of self and mutual inductance between the two sides. Now, in the previous chapter, we kind of treated it like we could start with one set of loops and then induce a current only using mutual inductance. But whenever we try and use mutual inductance, we're always going to have self-inductance happening at the same time. So we did some examples where we only included mutual, but in a transformer, it's going to be self-inductance, these coils interacting with these coils and reducing or creating a voltage drop. These coils interacting with these coils, creating a voltage drop. And then these coils interacting with these, creating an EMF, and vice versa. So once we include all those self and mutual inductances, we get to a set of formulas that look something like that. Okay, so we've spent a fair amount of time on transformers. I kind of like that because it gives us a chance to see how self and mutual inductance are related, and that you really don't have one without the other. Once you've introduced that second set of coils, both sides are going to have their self-inductance going on, and there's going to be cross-inductance, mutual inductance, happening in both directions, not just one. All right, so let's move on from that. There is this other example in here, and I think this is a pretty intimidating example. If you guys want to look at it, you're welcome to. I'm not going to say this is necessarily required. But you can go through and show that there's actually a certain amount of inductance built into wiring. So you can take, this example is taking a coax cable and getting an estimate as to how much self-inductance there is. So as the current increases or decreases, it's not going to increase or decrease rapidly, immediately. The inductance property of the cables means when I turn something on, it's going to take a while to build the current up. It's not going to happen right away. It's going to take a little bit of a delay depending on how much inductance is present. We talked about energy being stored in these inductors, and the energy storage in the inductors is stored as magnetic field energy. we've looked at electric field energy in capacitors and elsewhere, and now we're looking at magnetic field energy. These formulas don't come up, you know, it's not like they're coming up every chapter, but they are kind of persistent concepts that you want to be aware of. You want to be familiar with being able to calculate how much energy is stored. So here's an example that I threw in here. Potential energy. Now this is actually potential energy density. So, and I keep writing these units down to try and reinforce that idea. The formulas we're working from are in joules per cubic meter. So it's not just a straight energy calculation, it's how densely is energy packed into that region. And the textbook is going to start using mu naught and epsilon naught for these energy densities. But again, I'm going to argue that they can be written more simply and more systematically as 1 over 8 pi k times the electric field squared. Now, if I put numbers in for that, what I find is I'm getting units of joules per cubic meter. Also, the magnetic field energy formula looks exactly the same. Now, when you look at these energy density formulas with the epsilon naughts and mu naughts, they look different. They are different. But by writing the magnetic field not as B, but as C times B, that means that the CB now has the same units as an electric field. It's going to have units of newtons per coulomb, and then I can just use the very same formula and calculate the energy density. So let's try this. So I said, here's an electric field, and let's imagine this electric field region has a field magnitude of 400 newtons per coulomb. Well, using my electric field energy density formula, I can put in my 400 newtons per coulomb and square that, and then put 1 over 8 pi little k, where little k is my electromagnetic force constant. And that gave me 707 nanojoules per cubic meter. So 400 newtons per coulomb sounds like it's not a huge electric field, but it's not nothing. But the energy density there per cubic meter, that's a pretty good volume of space, still is just in the hundreds of nanojoules. So not especially large, not a huge amount of energy in this field. Now, if this field were going to go up by a factor of 100, then this energy density would go up by a factor of 10,000 because of the square factor here. How is the energy density going to compare with a magnetic field? And if we think in terms of C times B, then to get the very same energy density, I'm just going to say C times B is 400 newtons per coulomb. I plug that into the formula, the numbers look exactly the same. I'm going to have the same energy density. So let's see, what if we put the magnetic field back in Tesla? What would that look like? So it says that if I take this expression, divide it through by C, I get 1.33 microtesla. So I always feel like magnetic fields are a little shortchanged here, because when we represent them in Tesla, we get such tiny, tiny numbers for the magnetic fields. It's like, wow, 1.33 microtesla doesn't sound like anything. But when we multiply by C, so we can make a comparison with the E fields on an equal footing, we find out, oh, you know, a microtesla is like 400 newtons per coulomb. Or, yeah, 400 newtons per coulomb. That's a pretty sizable field. So anyway, that's a good comparison. And this potential energy density figures in with our inductors. So when we have inductors in a circuit, very quickly going back here. There we go. So when we have an inductor, what's going to happen is we're going to get magnetic field energy stored within that inductor. To find out the total amount of energy, we can do an energy density calculation and then multiply by the volume. So multiplying by the volume will tell us the amount of energy stored in the inductor. All right, let's start putting these inductors into some circuits. So we're going to start off with a circuit that has inductance and resistance in it. And surprisingly enough, we're going to call that an LR circuit. So here is what the circuit looks like. I've got a battery. It's got a voltage that's being designated as V0. And then I have a switch, and that switch continues through a circuit. Now there's resistance here, and there is inductance here. So I've got a resistor and I've got some inductance, and what's going to happen in that case is when I close the switch, the inductor is going to put up a fuss. So the inductor is going to oppose a rapid change in current. When you think about how we did circuits back in, say, chapter 26, what we had going on was when we closed the switch, immediately, instantaneously, there was a certain amount of current in the circuit. Well, that's not entirely realistic. When we turn on a circuit, there's always going to be a little bit of inductance in the circuit, even if it's just the inductance of the wires themselves. So there does require some amount of time in order to have the current reach its final value. So depending on how much inductance we put in, if we put a lot of inductance in, it's going to take a long amount of time for the current to reach its final asymptotic value. Now, here is the graph. So when we have an inductor and a resistor in a circuit, that effect of the inductor, instead of having the current jump immediately to some value, it's going to follow one of our upside down exponential functions. The asymptotic value for the current, eventually, the current still gets to be V0 over R, but it's going to take some time. And since this is, we'll see this is an exponential effect, or it's an exponential function, what that says is once one time constant has gone by, we're going to be at 63% of the maximum value. Now the time constant for these LR circuits is L divided by R. So it says the amount of time it's going to take, first of all, depends on how much inductance. If I've got a lot of inductance, it's going to take longer for the current to approach its asymptotic value. The process is going to be stretched out as I add more and more inductance into the circuit. Now the other thing is if I put a lot of resistance in the circuit, that actually shortens the time. And kind of the reason for that is, if I put lots of resistance in the circuit, well, that means that the Imax asymptotic value is going to be lower. If the value I'm eventually trying to reach to is much lower, that also is going to take less time. So the time constant depends on L over R, and that will determine how rapidly the current builds up in this circuit. So here are the formulas for this. So if we take a look at these formulas, what we've got is this. So they've got L d I dt. Now that's the voltage across the inductor. and they have R times I, well, that's the voltage across a resistor. So what that equation, the first one, is saying is that I have a battery. The battery is providing a voltage boost. So there's a voltage boost coming into the circuit, and that voltage boost is going to be equal to 2 voltage drops. So when we get this, this back EMF set up with the inductor, that we said was the equivalent of a voltage drop. And our formula for the voltage drop on an inductor is L di dt. If I solve this equation, I end up with this as a solution. Now, we've already seen an equation that looked very, very, very much like this, and that was the equation for charging a capacitor. When we charged a capacitor, what we found was that the charge on the capacitor followed one of these 1 minus e to the minus t over tau formulas, one of these flipped upside down exponentials. And then here, for the current, the asymptotic value is going to be V over R. And then for an LR circuit, and we've talked about this already, is that the time constant is L over R, and they really need to get rid of these periods on these equations. Don't need periods, right? Get rid of that, get rid of that, get rid of these guys. So that's the equation that it comes from. This is the solution, and let's look at some more diagrams showing how this is going to work. So we looked at what it would take to energize an inductor. Go back and look at that. So here we are energizing the inductor, and by energizing the inductor, we're building up current in the inductor, and the energy storage in the inductor is given by 1/2 Li squared. So there is a simple enough formula to tell me how much energy we have stored in an inductor. Now, the switch here is set up so that once we've energized our inductor, we can de-energize the inductor by moving the switch rapidly from here to here. Now, the idea here is if we do this quickly, the current will just continue. So we have to do this kind of instantaneously. If I instantly move from here to here with the current still moving, then the presence of this inductor says that the current will drop off slowly. It's a bit of an idealized circuit. When we charged the capacitor and then discharged it, it wasn't that difficult. You could imagine a capacitor charged, just sitting there with nothing connected to it. But you can't really have an inductor just sitting there with current going through it. So we have to kind of contrive a situation where the current never actually stops. So again, we got to switch that thing very quickly to make sure that the current never stops. Now if we do that, what happens is here is the de-energizing formula, and the current will drop off exponentially. So since it's an inductor and the current initially was going this way, the inductor hates changes in current. So what the inductor does is it starts with that current. It never switches directions. In this case, the current just ramps down. It just settles down to 0, following this exponential curve. It never changes directions. Same time constant. So if we've got the same amount of resistance de-energizing as we had energizing, then the time constant is still L over R. And since it's a straight exponential drop-off, one time constant will bring us down to 37% of the original current. So building up energy in the inductor and then releasing the energy out of the inductor. Once the current dropped off, all the energy is gone out of the inductor. All the energy that was stored in the inductor has been thermalized in the resistor. There's no more energy left in the circuit. So let's take a look at some numbers on this. Here is an LR circuit. Now, one of the key features that I'm going to say you really have to ask on every problem is, kind of my first question looking at a circuit is, what's the power source? And there's three possible answers to that. One of those answers is, it's a DC power source, and that's what we have here. We have a power source here that is DC, it's a battery. There's also going to be circuits we look at where there's no power source at all. And then finally, we're going to be looking at circuits that have an AC power source. And depending on how we're driving the circuit, if we're driving the circuit with a battery, versus do we have no power supply at all, versus is it an AC power supply, has a huge effect on how we analyze the circuits. So this is a battery, 12 volts. We're going to close the switch. There is inductance in the circuit, and so the current is going to increase asymptotically towards some final value. The numbers they've given us here, they're saying at t equals, they're kind of saying this incorrectly. At t equals 0, we close the switch. So I think that's what they want to say. We build the circuit, but we leave an opening for the switch, and then at t equals 0, we close the switch. And what that does is it connects into our circuit a 220 millihenry inductor and a 30 ohm resistor. Well, the numbers are right there. They want to know what's the time constant, telling us at what rate is the current going to be increasing, what's the maximum current, and how much time would it take to reach half of the maximum current, what's the rate of energy being delivered by the battery, what rate is energy being stored in the inductor's magnetic field. All right, that's a lot. That's an A, B, C, D, E, F problem, and I think I want to include G, so I have my own question that I want to add on to that. All right, but look, it fit on one page. Here is the LR circuit right here. There's the battery, it's 12 volts. Here is my 220 millihenry inductor. Here is the 30 ohm resistor. There's the switch. I'm going to close the switch at t equals 0. And what we saw, both by observation and kind of theoretically, we are predicting that the current is going to asymptotically approach some final value, and it's going to be represented by this 1 minus exponential function. There is the time constant right there, and what we found in solving that differential equation is that the time constant will be given by L over R. So I can put those values in. I put in the value for L, I put in the value for R. L was 220 millihenries, R is 30 ohms, and the time constant worked out to be 7.33 milliseconds. So those are thousandths of a second. That's not meter seconds, it's millisecond. And so I can use that time constant kind of throughout the problem. Now, let's step back over here. I'm kind of going back and forth from one side to the other in solving the problem. We've got the time constant figured out now. I can use that time constant, plug it in, and answer these first couple questions. At t equals 0, when we first close the switch, what's the current? Current's going to be 0, right? The current's starting off at 0, and so right here, we don't have any current at all. What is the maximum current that this circuit will eventually reach? And the maximum current is going to be given by V naught over R. That's 12 volts divided by 30 ohms. And that worked out to be 400 milliamps. So that's the amount of current eventually that will be running through this circuit. Now what they asked about was kind of what happens at when the current has reached half of its value. So I've got this 1/2 times the current, that's at 50%, and it's going to occur at some time shorter than the time constant. So I'm guessing it's going to be, the time constant here was 7.33 milliseconds. When I go in and solve for that, now what I'm solving for here is when does this go to 1/2? When does this factor become 1/2? And this whole thing is going to become 1/2 when this becomes 1/2, the exponential piece. So I just started with that. I said e to the minus t over the time constant. I'm going to set that equal to a factor of 2. Now I did a few lines of algebra here. I multiplied both sides by 2. Or maybe I should think of it this. I inverted the equation. This side, 1 over that became 2. 1 over this becomes e to the plus t over tau. And then I did a natural logarithm on both sides. The natural logarithm on both sides gave me an ln of 2. It undid the exponentiation. And then finally, t is equal to tau times the ln of 2. So practice that. If that's not familiar algebra, make sure you understand the steps involved in that. And again, logarithms are one of those things you come back to from time to time, and you kind of have to review how to logarithm algebraic manipulations work. Now the time that I got for the 50% mark was 5.08 milliseconds. Now I'm going to compare that with the 7.33, and I'm thinking, yeah, that seems reasonable. 5.08 milliseconds seems plausible compared with the other numbers that we've calculated. Now they've already told us that the current we're looking at right at that point is going to be 1/2 of the maximum value. So the current we're looking at is the 200 milliamps. So this tells me how much time it takes. This is the amount of current running at that time. Now once I know what the current is at that time, I can start calculating voltages. So I'm thinking I'm going to add more parts to this problem. Sorry about that. Or maybe that's good. Let's look at it a little more thoroughly. If there's a current of 200 milliamps, well, that's enough that I can determine the instantaneous voltage across my resistor. The voltage across a resistor is always going to be R times I. And I know what the R value is. That's 30 ohms. And I know now what the current value will be. And that says that the voltage across the resistor is 6 volts. So let's get our voltmeters. Here's the voltmeters. And I put my voltmeter here and it reads 12 volts. Now the switch is closed. I put my voltmeter here, it reads 12. I put my voltmeter here. This is variable and this is variable. Now it starts off with all the voltage here because there's no current. There's no voltage drop across the resistor if there's no current. So all the voltage starts at the inductor, and then as we have the current increase, more and more of that voltage shifts over to the resistor. And eventually, all of the voltage will be across the resistor. So when the current is halfway, then the voltage is halfway, and that says 6 volts. Now, what I'm guessing is, if this is at 6 volts, then this is going to be the remaining 6 volts, and we can go through and check that. For the voltage across the inductor, we can write that as L d I dt. So, and I apologize, some of this stuff is kind of scattered. This was the formula for I, and from this, I want to determine what's d I dt then. So d I dt would come from taking a derivative of this expression, and I can do that. If I take a derivative of that current expression, I get I naught. I bring down a factor of 1 over tau, and then I have a factor of e to the minus t over tau. Now there's a constant term here. there's a constant term here of 1, and taking the time derivative, that just goes away. So I'm only really taking a derivative of this side since this cancels out. And so what that tells me is the derivative of the time derivative of the current is given by this expression. I plug everything in, and I got 27.3 amps. Now, once I have the dIdt, 27.3 amps, I can multiply that by the 0.220 millihenries, and surprise, surprise, I get 6 volts on that side too. So it checks out. I've got 6 volts at that halfway point in terms of current. I have half the voltage on the resistor, the other half of the voltage is across the inductor at that instant. There's a couple more items here actually they're asking about. They're asking about power. Now they ask about power in the battery. What I went in and solved for was power in the inductor and power in the resistor very quickly. Any power calculation can be done as V times I. V times I works for every component, but I got to be really careful to get the V's and the I's correct. Now, the current that we're looking at is this 200 milliamps, and everybody's got the same current. It's only a one-loop circuit. And so everybody has, the battery has 200 milliamps of current passing through it, the inductor has 200 milliamps, the resistor has 200 milliamps. And then the voltages are also 6 volts each. So if I do V times I for the resistor, or V times I for the power, for the inductor, that gives me 1.2 watts for each one of those. So the two powers work out to be the same value. All right, so I'm going to stop there. Let's take a break, or let's stop, I guess, the lecture, and then we'll pick up probably with this example too, because there's just so much good stuff going on in this one particular example. We're looking at this pretty thoroughly.